Welcome to today's lecture. We're going to start chapter 12 today. We're going to mainly talk about vectors, points, operation between vectors. So let us start by defining coordinate planes. Definition. We are on 12.1, page 1. So officially we say that a coordinate planes consists of planes in three-dimensional space. Three-dimensional space. So remember that in two-dimensional space, you only have x-axis. Of course, you have y-axis. They are perpendicular to each other. And you have a bunch of points in this two-dimensional space. Some points, x and y. So this part, positive x values, positive y values, is called the first quadrant. First quadrant. This little part where x is negative, y is positive, is called the second quadrant. This part of two-dimensional plane where x is negative, y is also negative, we call it the third quadrant. The third quadrant. And finally, we have the last part, the last piece, which has positive x values, negative y values, we call it the fourth quadrant. Fourth quadrant. So this is for two-dimensional space, like a flat whiteboard. What if you're talking about our three-dimensional space here? In this case, we have x-axis, we have y-axis, and we can also add a new axis, z-axis. Very well. Of course, you can think about the intersection between x-axis, positive part of x-axis, and positive part of y-axis as x, O, y. Then you can think about the intersection of z-axis and the y-axis as a new plane, y, O, z, and a new plane, the intersection between positive part of x-axis and positive part of z-axis as x, O, z. So of course you can generalize the idea and talk about negative part of x-axis, negative part of y-axis, negative part of z-axis, and think about all of those intersections. XOY is also called XY plane. YOZ is also called YZ plane. XOZ is also called XZ plane. These form 8 octants. By using these planes, we can divide a three-dimensional space into 8 octants. Some notation for you. So remember that when you're talking about R is just a real axis. It can be either x-axis, or you can say that it's y-axis or z-axis. It doesn't matter. R is the collection of all points, of all numbers x, such that x is a real number. We can use the Cartesian product between R and form a two-dimensional space. A two-dimensional space has points with x and y values. So we define it this way. We say that R times R is equal to the set of all ordered pairs like x and y, such that x and y are real numbers. We usually denote this set by R squared. So R times R, or the Cartesian product between R and R, is denoted by R squared, the collection of all points in XY plane. The first quadrant, second quadrant, third quadrant, and fourth quadrant. In three-dimensional space, we have three coordinates, R times R times R, which is defined as the set of all points which has x, y, and z coordinates such that x, y, and z are all real numbers. X, y, z are real numbers. Well, as you guessed, we denote this by R to the third, and we say that, hey, they have a three-dimensional space. Another note for you. When you are working with graphs of functions in two-dimensional space, we usually refer to them as curves. And in three-dimensional space, we call them surfaces. So note, a function like y equals to f of x in two-dimensional space has a graph. This graph is called just a curve. So, for example, suppose you have y equals to x squared, and of course you can graph this curve, graph this function, x-axis, y-axis. This is y equals to x squared. You all know that it's just a parabola, opens up, and we call it a curve. Note, a function like z equals to f of x and y. Z depends on x and y in three-dimensional space. Of course, has a graph. This graph is called a surface. So remember that when you're talking about a curve, you're talking about a two-dimensional graph. When you're talking about a surface, you're talking about a three-dimensional object. Very well. Let us move on to the next page. Let us go over an example, see how to graph objects in three-dimensional space. Some simple examples for you. Graph the following. The first one says, hey, you have z equals to 3. The second one says, b, y is equal to 5. So let us think about it. Here you have the third variable z. It means that you are in three-dimensional space. So because of z, we are in three-dimensional space. So of course you have x-axis, y-axis, and z-axis. So x, y, and z. This equation says no matter what x or y are, your z is fixed and z is always 3. So it doesn't matter if I take xy here, or xy here, or xy here, my z is always fixed and my z is equal to 3. What's the meaning of that? It means that if I take any points, A and B, my z is 3. If I take another point, C and D, my z stays the same and it is 3. So it means that you have a graph passing through this point, 3, and it's parallel to xy point. This is z equals to a plane parallel to xy plane. For example, you want to graph z equals to 3. As you can see, here you have a plane, just a plane, parallel to xy. The next plane is y equals to 5. Y equals to 5. This is your plane. Well, you might say, okay, Professor, you say that y is equal to 5. What if I want to graph it in two-dimensional space? Of course, when I say that, okay, y is equal to 5, it's just a line. So in two-dimensional space, this equation, y equals to 5, is just a flat or horizontal line. Y equals to 5 is a line. So think about it this way. Here you have x-axis. Here you have y-axis in two-dimensional space, and y is always fixed. It doesn't matter what your x is, your y is always 5. So here you have this graph. The curve y equals to 5. But in three-dimensional space, this equation is equation of a plane. In three-dimensional space, y equals to 5 is equation of a plane. It's a surface in three-dimensional space. Another example for you. The question says, hey, now graph y equals to x in three-dimensional space. Graph y equals to x in three-dimensional space. So before graphing this, let's think about it algebraically. How do we graph this? In three-dimensional space, in R3, a surface y equals to x is the collection of points x, y, and z such that x, y, z are all real numbers. X, y, z are real numbers. So very well, what do I have here? This equation here says my x and my y, both of them are the same. Whatever x is, my y is the same as that x. So this collection, this set, is the set of all points x. Instead of y, I'm going to write x because y and x are the same, comma z, such that x and z are real numbers. Think about it this way. Here, for example, you have your x, here you have your y, here you have your z. X and y are the same. 1, 1, z. 2, 2, z. 3, 3, z. Negative a half, z, and so on. This is y equals x, y equals to x in two-dimensional space. Now, whatever your x, your y, they are the same, or your z assumes a different value. 1 and 1, 0. 2 and 2, for example, 10. Anything. Let's take a look at the graph together. X equals to y. Very well. So this line is y equals to x, and you have a plane passing through z-axis. This is the graph of y equals to x, or x equals to y in three-dimensional space. Very well. Let us move on to the next stage and talk about the distance between 2 points. Let us get back to Calc 1. Recall, in Calc 1, we learned that if P1 is a point in two-dimensional space, x sub 1, y sub 1. And P2 is another point in two-dimensional space, p sub 2, x sub 2, y sub 2. So you have 2 points, P1 and P2. We can find the distance between these 2 points. The distance between these 2 points, absolute value of p sub 1, p sub 2 is equal to square root of the difference in x values, x sub 1 minus x sub 2 squared, plus the difference in y values squared, y sub 1 minus y sub 2 squared. This is the distance between these 2 points, absolute value of p sub 1, p sub 2. So, of course, we can generalize the idea having 2 points in three-dimensional space. Now we have to add z as the third coordinate. Now, for 2 points, P1, S sub 1, Y sub 1, and Z sub 1. And the second point, P sub 2, X sub 2, Y sub 2, and Z sub 2 in 3-dimensional space in R3. The distance is defined as, so the absolute value, P1, P2, the same, square root of the difference in x values, x sub 1 minus x sub 2 squared, plus the difference in y values, y sub 1 minus y sub 2 squared, plus the difference in z values, z sub 1 minus z sub 2 squared. One example for you. Example says, find the distance between these 2 points. Find the distance between these 2 points. The first one is 2, negative 1, 7. Was 1, 2. 2, negative 1, and 7. And the second point, P sub 2, is, let's say, 1, negative 3. And they have 5 here. Perfect. So let's label each of these for simplicity. Here you have x sub 1, y sub 1, z sub 1. Then here you have x sub 2, y sub 2, z sub 2. Okay, let's just follow the formula. The distance between P1, P2 is square root of 2 minus 1 squared plus negative 1 minus 3 squared plus the difference of z values, 7 minus 5 squared, which gives you square root of 1 squared, which is 1, 1 minus 3 minus 1, 2, plus 4, 7 minus 5, 2 squared, which is 4. You get the square root of 9, or 3. Okay, now question says, find equation of a sphere in 3-dimensional space, center, and the point C, H, K, and L with radius R. Okay, let's think about it this way. We have a sphere in 3-dimensional space. So if you have X, if you have Y, if you have Z, then here you have a sphere in 3-dimensional space. So you have a radius R. I suppose the center is here. This is your radius. And this is the center here. So. Okay, very well. How do we write the equation of a sphere from scratch? So if we think about it this way, what's the distance between C and any point on the sphere? Take a random point like X, Y, Z on the sphere. We find the distance between that point, X, Y, Z. Just put X sub 0, Y sub 0, Z sub 0, it doesn't matter. You can just say that it is X, Y, Z. Find the distance between this point and the center C, H, K, and L. And at the same time, you know that this distance is defined as R. So the distance for R is equal to square root of X minus H squared plus Y minus K squared plus Z minus L squared. Now square both hand sides to get rid of the radical. R squared is equal to the difference in X values, the difference in Y values squared, plus the difference in Z values squared. So this is equation of a sphere centered at H, K, L with radius R. Okay, example. So question says, show that this equation, x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equal to 0 is equation of a sphere and find the radius and the center. Perfect. Very well. Here you have equation of a sphere in expanded form. Our goal is to write it in compact form. So this is our goal. Our goal is to write this equation in the form of x minus h squared plus y minus k squared plus z minus L squared equals to R squared. Very well. Let us start. So what do you have here? You have x squared, you have 4x. X squared plus 4x. You have y squared negative 6y plus y squared minus 6y. You also have z squared plus 2z. Z squared plus 2z. And finally, you have a constant plus 6 equal to 0. We're going to complete the square and write each of these in the format that we can convert them into a complete square. So remember that to complete the square, if you have x squared plus bx, you take b, you divide by b by 2, and you square it, and you add and subtract b half squared, and you take these three terms, and you have x plus b half squared, you can write it in compact form, minus b half squared. So this is our goal. You need to identify your b divided by 2, raise the whole thing to the second power, so you have 4, divided by 2 is 2, 2 squared is plus 4 minus 4. Then you have y squared minus 6y. Take 6, 6 divided by 2 is 3, 3 raised to 2 is 9, so we add and subtract 9. Now for z squared plus 2z, b is 2, divide b by 2, you get 1, 1 squared is 1, we add and subtract 1. Okay, now we take these three terms, we have x plus 2 squared minus 4, plus we take these three terms, y minus 3 squared minus 9, we take these three terms, plus z plus 1 squared minus 1 plus 6 equal to 0. I have some constants. Let's combine them together. I have x plus 2 squared plus y minus 3 squared plus z plus 1 squared. Negative 4 minus 9 is equal to negative 13, negative 14, plus 6 is negative 8. So it is equal to 8. Very well. Let us compare this equation with the original equation that we have. Here you must have x minus 2 squared. Why is that? Because you're forming x minus h squared. So h is negative 2. Plus, we don't have any problem with the second term. It is plus y minus 3 squared. So here you have y minus k squared. So k is positive 3. Plus, okay, we have a plus sign. We should be careful a little bit. Plus z minus 1 squared. So if you compare it with z minus l squared, as you can see, l is equal to negative 1. This is your l. Equals to r squared. R squared is equal to 8. So r, the radius, is equal to the square root of 8. And the center, as we found, is negative 2, 3, and negative 1. Okay, guys, take your time. Write this down. So take a look at this sphere in three-dimensional space. I'm using GeoGebra to graph it. As you can see, the center is not at the origin. The center of the sphere is -2, 3, and -1. You can actually just rotate this. And actually, you can see that this sphere is below, almost the majority of this sphere is below XY plane. Here we go, another example for you. This example says, so what region in R3 is represented by the following inequalities? What region in three-dimensional space is represented by the following inequalities? So here you have x squared plus y squared plus z squared sandwiched between 1 and 4. What else do we know? We know that z is. Okay. So let's discuss this first, then we add another condition. First of all, we call that equation of a sphere. X minus h squared plus y minus k squared plus z minus l squared equals to r squared is a sphere with center at h, k, l, and the radius equals to r. And we know how to graph. So here you have x-axis, here you have y-axis, here you have z-axis. If the center is the origin, if C is 0, 0, 0, or the origin, then the center is located here. And for your sphere with radius r, you get a sphere like this. Okay, very well. R, and R. The distance is plus R. So, how do you describe all inner points? How do you describe all outer points? So note that. Note that. If you say that I have x minus h squared plus y minus k squared plus z minus l squared less than or equal to r squared, you're talking about the solid sphere. This is going to be x-axis, this is going to be the y-axis, and this is going to be the z-axis, and here you have your sphere. And all points, all values inside the sphere. So you shape all of these points inside the sphere. So if I flip this inequality, I'm talking about all points outside the sphere. Okay, now you can just work with these. When you're talking about x squared plus y squared plus z squared greater than equals to 1, you're talking about all points outside or on the surface of sphere centered at the origin with radius 1. So all points on the surface or outside the sphere. When you're adding less than equals to 4, you're talking about all points on the surface or inside on the surface or inside the sphere with radius 2. So think about it this way. Let me erase this. X-axis, Y-axis, Z-axis, 1 and 2, 1 and 2, 1 and 2. So you're actually looking at all the points in between two spheres. The inner sphere is a unit sphere. Sphere with radius equals to 1. Radius is 1. And the second sphere is the outside sphere, outer sphere, with radius 2. So all the points in between these two spheres are the solutions for these inequalities. So let's talk about objects in two-dimensional and eventually three-dimensional space other than points, so we can form vectors. Vectors in two-dimensional and three-dimensional spaces. There you go. So let A comma B be a point in xy plane. So if you have a point in xy plane, you all know that you can form a new object that we call a vector. X-axis and y-axis. This is your point A, comma, B. Okay, we can connect this point to the origin and we define a new object that we call vector B. Usually put a direction bar on B to show that we have a vector. Then we can form a new object, a vector now. Suppose we have two vectors in xy plane. So suppose your first vector is v and the second vector is u. What we can do, we can add these together, we can subtract them, and eventually we can define other operations in between two vectors to form a new object. We can add these two objects or subtract them. So suppose your vector v is equal to a and b, and vector u is equal to c and d. V plus u is equal to a comma b plus c comma d. To add these two vectors, you just add the first coordinates, you add the second coordinates, a plus c comma b plus d. Of course, when it comes to addition, ordering is not important. It's the same as vector v, vector u plus vector v. We can also subtract this. Vector v minus vector u is equal to a b minus c d, which is the difference between x values, the difference between y values. A minus c, comma, b minus c. Note that it's not the same as u minus b. In general, they are not equal to each other. Very well, and we also have something that we call scalar multiplication. Scalar multiplication. Suppose you have just a scalar. Let me just follow. Think of c as a scalar. C is just the coefficient, is just the number times vector v. This is defined as c times a comma b, which is ac comma c or bc. It doesn't matter. C is a number. So let's take a look at two vectors. The first vector, for example, is a, b with coordinates 5, 7, 8. The second one is ba, which is -5, -7, -8. As you can see, they have the same magnitude, but they are in opposite direction. If you add these two vectors, the sum is equal to 0. So the magnitude of these two vectors are the same in exact opposite direction. Okay. Magnitude or length of a vector. Definition. Sometimes they call it norm as well. So if you read a word norm in a book, it's talking about the magnitude of a vector. Definition. The magnitude or length or norm of a vector. Suppose we're talking the same vector. Of a vector like a, b, which is x2 minus x1, y2 minus y1, and z2 minus z1 is defined as, so we usually put it inside absolute value. Sometimes they use two lines. So the norm or magnitude of a vector a, b is defined as square root of the first coordinate squared plus the second coordinate squared plus the third coordinate squared. This is the magnitude or norm or length of the vector. So let's go over a couple of examples to feel comfortable about the whole thing, what's going on here. So this example says, suppose you have A equals to, A is just a vector, 4, 0, 3, and B is another vector for you, -2, 1, 5. You can put a bar on top of A and B to make sure that you have a vector. It says find the following. First of all, find the length or magnitude of A. Then find A plus B. Then find this new object, the subtraction between them. Then find 3 times B, the scalar multiplication. And finally find 2A plus 5. There you go. Let's follow the definition of magnitude or norm of vector A. You take the first coordinate, square it, plus the second coordinate square, plus the third coordinate square. So we get square root of 16 plus 9, or square root of 25, or just 5. So the magnitude of the first vector is equal to 5 units. What's the sum between these two? The sum between x values, sum between y values, and sum between z values. This is 2, 1, and 2. And you write. Now it says find the difference between these two vectors. A minus B, so 4 minus 2, comma, 0 minus 5, comma, 3 minus 5. 4 minus 2, which is 6, -1, and -2. Scalar multiplication, 3 times vector, it is 3 times vector B, which is -2, 1, and 5. We have to multiply all of these coordinates by 3. Or you can say that I'm going to distribute 3. You get -6, 3, and 15. And finally, 2 times A plus 5 times B. 2 times the first vector, 4, 0, 3, plus 5 times the second vector, -2, 1, and 5, which is equal to, so 2 times 4, 8, minus 10, comma, 2 times 0, 0, plus 5 times 1, and 2 times 3, 6, plus 25. This gives you -2, 5, and 31. So I'm going to write a note for you. For example, suppose you have a vector. Let's write a note here for you. For a vector like V equals to, let's write its elements as A sub 1, A sub 2, A sub 3, and so on Then we call these numbers the components of vector V. So this is your first component. A sub 2 is the second component. The third component, and so on. Definition of standard basis vectors. Standard basis vectors. So I expect you to ask, when you're talking about x-axis, y-axis, how do you present those axes using a vector? Okay, suppose you have x-axis and y-axis. And suppose we add z-axis as well. To present the direction on x-axis, we use vector I with magnitude equals to 1. To present y-axis, we use vector j with magnitude 1. And for z-axis, we have vector k. I, j, and k. These are all unit vectors. We define unit vectors I, which is defined as the first component of the vector is 1, the second component of the vector is 0, and the third component of the vector is 0. As you can see, the length of this vector is equal to square root of 1 squared plus 0 squared plus 0 squared, which is square root of 1, equals to 1. So that's why we say that it is a unit vector. Unit, it means that its length, its magnitude is equal to 1. And vector j, 0, 1, and 1, and vector k, which is defined as 0, 0, and 1. All of these are unit vectors. If you find the length of these vectors, it's just 1. And for vector k, the length for normal vector k, 0, 0, 1, which is square root of 1, or 1. All of these are unit vectors. So any vector like v with components a, b, and c can be written using I, j, and k. This is a in the direction of x-axis plus b in the direction of y-axis plus c in the direction of z-axis. A, B, C, A on x-axis, B on y-axis, and C on z-axis. There you go. So I expect you to ask, what if I don't have a unit vector? How can I form a unit vector? This is important, especially when you're taking Math 1D. There you have to form unit vectors. Note, let V be any vector. We can take V and define a unit vector by dividing components of V by magnitude of V. So U, a new vector, is vector V divided by the norm magnitude of V, which is defined as A divided by magnitude of V, comma, B divided by magnitude of V, comma, C divided by magnitude of V. You all know that how to find the magnitude of V. This is equal to A divided by square root of A squared plus B squared plus C squared, comma, B divided by square root of A squared plus B squared plus C squared, and comma, C divided by square root of A squared plus B squared plus C squared. This vector is a unit vector. Know that. The magnitude of this new vector is equal to 1, so you have a unit vector. So U is a unit vector. Very well. Here you have a vector. And you're going to transform that vector into a unit vector, a vector with a length 1. So example, let V be a vector 2, -1 and -2 for a unit vector. Very well. To form a unit vector, let us call this new vector U, unit vector. It is equal to, we take the components of vector V and we divide them by the magnitude of V. So your goal is to find the magnitude of V. The magnitude of V is not very hard to find. The magnitude of V is defined as square root of 2 squared 4 plus 1 plus 4, 4, 4, 8, 9, which is 3. So your unit vector is equal to 2 divided by 3, -1 over 3, -2 over 3. We can leave it as it is, or you can write it this way. This new vector is a third times 2, -1, -2, or a third times vector V. You can check to see if the length of U is equal to 1 or not. You can check it. So the length of U is equal to square root of 2/3 squared, 4 over 9, plus a third squared, 1 over 9, plus 2/3 squared, which is 4 over 9, which is square root of. They all have the same denominator. You write one denominator and add the numerators. 4 plus 1 plus 4, which is square root of 9 over 9, or